Okay, welcome to the next one. You can see we're going to run through two learning intentions this time because they're both very short. Be able to explain and apply work and force versus distance graphs, and be able to explain and apply Hooke's law and elastic potential energy. So neither of these is too complex, and we will do a prac to go with the second one. So work done. I know you've done this in the past, so we'll just express it in a slightly better version. We know that from the past. We also know work, so we'll call it W for now, equals sigma fx from the idea that work equals force by distance, which I know you've done in the past. Right, and I do that with my year 10, so I know you've done it at some stage in the past. The difference is the sigma f is the effective force in the direction of motion. So you've got to remember that it is the effective force, but there's also a few other things you can add on there. Work is the change in energy. So we know it's measured in joules. Now let's do that other little bit that goes with this, which is force distance graphs. Now, as was explained in the previous video, anything where there is a linear relationship with two quantities that multiply each other, the area is automatically the subject of the equation. So in any force distance graph, the area is the work done. That's that is particularly applicable when we change over to the springy stuff, which we'll do now. Hooke's law we're going to follow up in class with a prac, but we'll have a quick look at it now. So, Hooke's law is to do with elastic things. So, and when you have a force versus distance graph for an elastic object, but this is particularly, we should graph extension. Extension, of course, being the change in length. When you graph the change in length for an ideal spring, you get a straight line graph through the origin. So, but we should be keeping noting that this is an ideal spring or an ideal piece of elastic. Real ones don't have quite such perfect graphs. Okay, and we know from our understanding of mathematics that it's going to be a very simple relationship. And I'll explain what the minus is to do in a minute. F equals minus kx, where k is the spring constant, which is the gradient, and which is also the gradient, and that would be Newton meters to the minus 1. X equals extension, so that's the change in length. Okay? So, let's quickly change pages and talk about just a couple of other things to do with springs. Now, we know from what we talked about earlier when we got any sort of real object, so any sort of thing where we've got the two quantities multiplying each other, and it's a simple linear relationship, we know that the work done equals the area under the graph. In this case it's work equals force by distance. The work equals force by distance is also the energy stored in the spring, which is the same thing. So U spring equals a half Fx because it's a triangle, and F equals Kx. We can ignore the negative, and we'll talk about the negative in a minute. So that work equals U spring equals a half Kx squared. In that original equation of F equals minus Kx, the negative is due to direction. Nothing to do with a linear relationship, nothing to do with negative gradients, it's only to do with direction, nothing to do with the mathematics at all. Only one other thing we want to look at quickly with springs. It's to do with much more closely to real springs, which we'll see in our prac. And the complications come when we start talking about energy interchanges with these springs, but we'll talk about that in class. Okay, if any sort of springy system, especially something like a rubber band, tends to start with a fairly straight area and then tends to move upwards. That's because it becomes much more difficult to actually extend. Where it changes direction is called the elastic limit. Once we reach this part up here of the graph, the example, so example rubber band or spring, cannot return to the original shape. So it's impossible for it to return to the original shape at that point. Okay, so the thing about energy interchange of springs we'll talk about in class. Kind of just mention it maybe here, but if we're hanging, we'll pretend there's a nice solid barrier across the top. If we're hanging a spring from a barrier and we've got a mass on it, so we'll use the same colour for the spring the whole time. And we've got a mass stuck to the spring. And it's just sitting there. We know that there's spring potential energy involved. If we then lift that mass and let it go, we know that that mass is actually going to oscillate. So that mass is going to oscillate upwards and downwards around that center point from before. So where it was resting before will be the center point of the movement. So when it's at the top, it's all U gravitational. When it's at the bottom, it's all U spring. When it's in the middle and anywhere in between, it's kinetic, U gravitational and U spring. So there's a really interesting interchange between the three energies, but obviously the total energy is always the same. It's that sort of interchange that was asked in detail last year on the exam, and we'll talk about that in detail when we both do our prac and in class. Okay, that's the end of this one.